as we've seen in the previous segment, the Stern-Gerlach experiment confirms some aspects of the Bohr model, in that it did seem to confirm that at least silver atoms had a magnetic dipole moment. But as things progressed, by 1926, Schrodinger had introduced and solved the quantum mechanical hydrogen atom wave equation, and we had a new and improved model of the atom, at least in some regards. And so it's appropriate to look at that in the context of the Stern-Gerlach experiment. Remember, we had this force that was produced on a magnetic dipole Z component, mu z, force in the z direction. That's really the relevant one. The thing that's new in Schrodinger wave mechanics is that we have the z component of the angular momentum quantized in units of m sub l times h bar, where m sub l is the magnetic quantum number that goes from 0 plus or minus 1 up to plus or minus L. And if we put the orbit of the atom in the xy plane perpendicular to the z-axis, then the orbital, the z component of the angular momentum is r times p, or r mv is m sub l h bar now, not n like in the Bohr theory. One again can solve this for v. The momentum is just mass times the velocity. Solve for v. Did that exactly the same as before. The only difference is that we had n here instead of m sub l, and n goes 1, 2, 3, 4, etc. And in our case, the m sub l's could take on these values from plus or minus L down to 0. So again, do the same formulas as before. The current is the charge that passes in a time delta t. If we count the charge, one electron of charge passes in one orbital period. An orbital period is just 2 pi times the radius divided by the velocity. The distance traveled divided by the speed will give us the time of the orbit. And we got exactly the same equation as before. And now then we plug this into here for v and simplify, getting this. So now I get a 2 pi r squared, m sub l, the quantum number, m sub e, the electron mass. And then to get the magnetic moment, it is simply I a, and the area is pi r squared. The pi r squareds go out. And again, we get a slightly different expression now. We get that the magnitude of the magnetic moment is the Bohr magneton times m sub l instead of n. And that's all of it, since it's perpendicular. That's the z component. And so the force in the z direction is mu z times the derivative of b with respect to z. And then simply plug this into here. And now then you see that the force gets quantized into 3 pieces. Well, I say 3 pieces. If L is 1, I get an L equal to 1, L equal to minus 1, and an L equal to 0. And so one expects now to get 3 separate dark lines on the glass plate when we pass through. The big advantage here of this is it showed people that how you could actually get discrete lines on here and not have a continuum like was predicted via the Bohr theory. So they thought that that was promising. However, no matter what the value of L is, you're always going to have an odd number of lines here. Either if M sub L is 0, you only get 1. If M sub L is plus or minus 1, if L is 1, you get 0 and plus or minus 1. That's the one I drew here. But you'll always get an odd number. The total number of lines is always an odd number. Moreover, a bigger problem. And that wasn't what it was observed, I should say. And a bigger problem, in fact, was this. If you look at in sort of modern day notation, silver atom is atomic number 47, which is a krypton core, and then the outer shell is 10 4d electrons and 1 5s electron. And the outer shell here, all these others are closed shells. So the outer shell electron is, in fact, S is an L equal to 0 state, so the only value of M sub L in this case is 0. So for 0, you would expect to get no force and no splitting. And so one expected this, and in fact you observed the two-line spectrum, two-line splittings. Now, again, they curve over on the side, but those are due to edge effects. The central portions are basically straight lines across. So in some degrees, the full quantum mechanics pointed people in the right direction, but it didn't solve the problem because it was expecting an odd number of lines. But at least it showed how you could get lines instead of a continuum. And it certainly has an issue in that it predicts really nothing. So in that regard, I guess it's even worse than the Bohr theory. At least the Bohr predicted some spread in between these, but a continuous patch. But what was in fact observed was really just two straight lines across, two deflection paths. Well, we'll look at how that gets addressed in the next segment. At least the way that Gerlach and others did it. But we will continue from here next time.